So, in this lecture, I am going to talk about how we can understand continuity of functions in terms of sequences. In other words, sequential continuity. So, the main theorem is the following. Suppose f is a function from I to R, where I is a subset of R containing a neighborhood of a point A. Now, we are going to characterize the continuity of f at A in terms of sequences. So, we say then f is continuous at A if and only if for every sequence xn in I, all these points x1, x2, x3 are in I, such that limit as n tends to infinity xn is equal to A, the limit as n tends to infinity f of xn is equal to f of A. The proof is fairly straightforward. You just see what you need to prove and then use the hypothesis to prove it. So, there are two things to prove. Firstly, let us suppose that f is continuous at A. And suppose xn is equal to A. Now, I want to prove that the limit as n tends to infinity f of xn is equal to f of A. So, I need to show that given any epsilon greater than 0, so let us do some rough work over here. So, what do I want to do? I want to make f of xn minus f of A small. But because f is continuous at A, I can make sure that this is small. There exists delta greater than 0 such that if xn minus A is less than delta, then f of xn minus f of A is less than epsilon. But now, since the sequence xn itself converges to A, I can choose a natural number n such that if n is greater than n, then absolute value of xn minus A is less than delta, by taking this delta to be the epsilon for the convergence of the sequence xn. So, let us work it like this. Given epsilon greater than 0, choose delta greater than 0 such that x minus A less than delta implies that fx minus fa less than epsilon. And now, since the sequence xn converges to A, choose n in n such that if n is greater than n, then xn minus A is less than delta. So, then what we have is, if n is greater than n, xn minus A is less than delta, which implies that f of xn minus f of A is less than epsilon, which is exactly what we had to prove. We have shown that the sequence f of xn converges to f of A. Now, for the converse, note that what we are saying is that for every sequence xn that converges to A, f of xn converges to f of A. We will need this, crucially this fact that this is true for every sequence. So, the way the proof goes is by contradiction. Suppose we can find even one sequence xn in I such that limit n tends to infinity, xn is equal to a, but limit as n tends to infinity f of xn equal to a does not hold. What does it mean to say that this statement here does not hold? Well, it means that there exists epsilon greater than 0 for which there is no delta. For every delta greater than 0, you can find there exists a point x delta such that x delta minus a is less than delta, but f of x delta minus f of a is greater than epsilon. Consider the sequence x 1 over n. Now, what we know is that x 1 over n minus a is less than 1 over n by the choice of x 1 over n. And so, we have limit n tends to infinity of this sequence x 1 over n is equal to a. However, f of x 1 over n minus f of a is greater than epsilon for all n belonging to n. So, this means that limit as n tends to infinity f of x 1 over n equals f of a does not hold. Continuous functions on closed intervals have some very nice properties, and one of them is that a continuous function on a closed interval is bounded. So, suppose f from a closed interval a b to r is continuous, then f is bounded on a b, which means that there is a bound, there exists some real positive number k such that for all x in the closed interval a b, all x between a and b, a less than or equal to x less than or equal to b, absolute value of f of x is less than k. This is not true for functions defined on, for example, open intervals. So, look at the function f defined from the open interval 0 1 to r given by f of x is equal to 1 by x. This function is perfectly well defined on the open interval 0 to 1 because 1 over x is defined for all non-zero real numbers x. But if you look at the graph of this function, what does it look like? Well, the graph looks something like this, and you see that as x gets closer and closer to 0, this function gets larger and larger. Given any k positive, take x to be the minimum of say half and 1 over 2k. So, then this x will certainly lie between the 0 and 1 because I do not allow it to be larger than half, and f of x, well, that is going to be 1 over x, which will be greater than the maximum of 2 and 2k, which will certainly be greater than or equal to 2k. And so, what we have is that the absolute value of f of x is certainly not less than k. So, this function here is not bounded, but when your function is continuous on a closed interval, if we could have extended this function continuously to the point 0, then it would have been forced to be bounded. Let us give a proof of this. So now we will again argue by contradiction. Suppose f is not bounded, we will find a point where f is not continuous. Then that means that no positive real number is a bound, which means that for every integer n, there exists a point xn in the closed interval a b such that absolute value of xn is greater than or equal to n. So, we are just saying that n is not a bound for f on the closed interval a b. So, now we have the sequence of real numbers in the closed interval a b. So, by the Bolzano-Weierstrass theorem, remember the Bolzano-Weierstrass theorem said that any sequence inside a closed interval has a convergent subsequence. There exists a subsequence xnk of xn that is convergent. So, let us say that a is the limit of this subsequence, limit as k goes to infinity xnk. Then by sequential continuity, what we have is that limit as k goes to infinity f of x n k is equal to f of a. So, the sequence f of x n k is a convergent sequence, hence it is bounded. But this is a contradiction to the choice of x n k. We said that f of x n k should be greater than or equal to n k for every k, which means that it is an unbounded sequence. We have seen that continuous functions on closed intervals are bounded. In fact, we can show that those bounds are actually attained, that they have maximum value and minimum value on the interval. Theorem: suppose f is a function from a closed interval to R which is continuous. Let m be the supremum of the set of values of f on the interval a b. Remember that the set of values of this function is a bounded set, and therefore it must have a supremum or a least upper bound. Let m similarly be the infimum of f of x such that x belongs to a b. Then you can actually find points x max and x min in the interval a b such that f of x max is equal to m and f of x min is equal to little m. In other words, for every x in AB, we have f of x lies between f of x min and f of x max. It is important to note that this property will not hold if we look at an open interval instead of a closed interval, as this very simple example shows. Just take f from 0, 1 to r given by f of x is equal to x. Then the set of values taken by this function are all the real numbers that lie strictly between 0 and 1. So, m is equal to 1, little m is equal to 0. But the function does not take the values 0 and 1 on any point that is strictly between 0 and 1. Okay, now let us prove this theorem that every continuous function on a closed interval a b attains its supremum and infimum. So, now remember that m is the supremum of f of x, x belongs to a minus a comma b, which implies that for every natural number n, there exists a point xn in a b such that f of xn is greater than m minus 1 over n. And of course, since m is an upper bound for the values of f, m is greater than or equal to f of xn. And this implies that absolute value of f of xn minus m is less than 1 over n. By the Bolzano-Weierstrass theorem, implies that this sequence xn admits a convergent subsequence. X of nk. Let c be the limit as k goes to infinity x of nk. So, we have f of c, well, this is f of the limit as k goes to infinity x of nk, but by sequential continuity this is the same as limit as k goes to infinity f of x of nk. But remember, x of nk is within a distance 1 by n of m. So, this limit has to be equal to m. So, what we have shown is that there is a point c where the function takes a value m. So, we can take this c to be x max. A very similar argument shows that f also attains its minimum value on the closed interval a b.